Hi, everyone. Welcome to our session today. We're so excited to have you here with us for a session on exploring alien worlds from science fiction to science fact. We're especially excited to be talking to you right now. As many of you may have noticed, the recent releases from the James Webb Space Telescope with some of the earliest data of their data from some of these new exciting exoplanets. Before we dive in, we want to do some introductions for our day. My name is Erika Wright. I am from the Center for Astrophysics, which is actually a collaboration of the Harvard College Observatory and the Smithsonian Astrophysical Observatory, which is one of the Smithsonian's research arms. Many are familiar with the museums, but we're one of the centers solely focused on discovering new information about our universe. And I'm an education specialist there. Today with me, I have Mary Dussault. Mary, you want to introduce yourself?
Sure. Thanks, Erika. I'm a science education program manager here at the Smithsonian Astrophysical Observatory, part of the Center for Astrophysics. And on screen, I'm a white woman with blonde hair. I'm wearing a green shirt and glasses. I'm sitting in my office with bookshelves behind me. And I'm really looking forward to today's discussion of alien worlds.
And we have Mercedes López-Morales. Mercedes, would you like to introduce yourself?
Yeah, thank you, Erika. Hi, Mercedes. I am an astronomer at the Center for Astrophysics, Harvard and Smithsonian. And, I have black hair, I have glasses, I'm very short, I'm only 4'10". And right now I'm sitting in a kid's bathroom in my in-laws' house in Scotland because we're here on vacation. So I came back from my vacation, looking forward to telling you what we do on exoplanets.
Wonderful. And we really appreciate you taking a little break from your vacation to be here with us, Mercedes. We're really excited about it. And both of you reminded me, I forgot to give it a quick description of myself. I am a white woman with brown hair sitting in front of a yellow wall with a nice pastel painting behind me. So to start us in on what we're actually going to be doing today, I think we'll put up our first slide, give a little introduction of our journey. So today, we've just done some brief introductions. In a moment, we're going to give you take some initial ideas on alien worlds. What are they? What do we think of? How do we imagine them? Then we're going to hear a perspective of an exoplaneteer, Mercedes, and she's going to tell us a little bit about what the astronomy is like that she does and how she discovers and explores exoplanets. Then we're going to dive into the DIY or do-it-yourself planet search online laboratory that's designed specifically for educators and learners to explore exoplanets on their own. And we'll tell you a little bit more about how you can engage your students in that. And we'll have a few moments, opportunities for Q&A, both after Mercedes' presentation and at the end of the session. But now we're going to dive into our first slide. Mary's going to introduce you to one of her favorite images.
Great. Thanks, Erika. Yes, so I wanted to get our minds open and curious and thinking about space and other worlds with this favorite image of mine, which is a NASA image of a real alien world. In fact, this image contains the only planet where life forms have been discovered. And in fact, we even think intelligent life resides there. Now, some of you may be a little confused as you're looking at this image. Next slide, please, because you're thinking, this is an image of Saturn, isn't it? And it is. That's not the alien world I'm talking about. This image of Saturn taken from the Cassini image, taken from the Cassini satellite with the sun's kind of backlighting Saturn here. But the alien world I'm talking about is, next slide. There is us. This is an image of everyone in this session. It's an image of you. It's an image of Earth. There's a tiny blue dot that is Earth in this image taken from the Cassini satellite. And in fact, if Earth were an alien world for some other solar system looking back at our solar system, and if other intelligent beings in another world were investigating our solar system, they would have to deduce the characteristics of Earth from an even weaker signal than the tiny blue dot that we get to see from the Cassini satellite. So I think one of the things I think is amazing is how much we can learn by being light detectives. And that's what we're going to find out today. Open your minds to thinking about, learning about what's out there in space. And by the end of the session, we hope you'll be inspired to detect and investigate one or more of these alien worlds in other solar systems with your own students. Next slide. So, in fact, since 1995, this is a new science detecting exoplanets. Since 1995, astronomers have discovered more than 5,000 planets orbiting other worlds beyond, orbiting other stars beyond the solar system. And it's an amazing diversity of worlds that have been discovered. Great big gas giants orbiting close to their stars, rocky planets, water worlds, hot lava planets, amazing diversity of worlds. And just based on the statistics, scientists think when you look in the night sky, almost every star you see has on an average a planet orbiting it. So given that, next slide, please. I want to just pause here and have a moment to think. Erika?
Yeah, Mary and I have Mary's just described to us this little introduction to exoplanets or other worlds out there. And we want to take a minute to hear from you about what questions, ideas, what thoughts are starting to bubble up in your brains about exoplanets. What do you think of? What do you imagine when you hear that word, when you hear other worlds? I know one of my first things that always comes to my mind when I start thinking about exoplanets. I'm actually a big science fiction fan. I'm a big fan of Doctor Who, and I love imagining the worlds that they visit on that show. There's such a diversity of planets and systems that they explore. Also, the life that they explore on these planets are so unlike the life here on Earth. What might it be like? So what are some of the things that you think of, or maybe that you imagine your students might think of when they think of exoplanets or alien worlds? Mary, what's one of yours?
Well, I am a bit of a historian of science. And when I think of the history of science, the idea of asking, are we alone and are there other worlds out there, has been asked for a long time. And I actually was thinking recently about Giordano Bruno in the 1500s, actually around Copernicus's time, was deciding that all those stars could be other suns with worlds going around them. And that was considered radical thinking at the time. And I think radical thinking is what science is all about. And so that's one of the things I think about in terms of imagining other worlds.
That's amazing. We're seeing some answers in the chat here, and this one is very exciting and I think pertinent to some stuff that Mercedes might share with us later. One of our viewers out there is thinking about chemical elements and how life outside of our universe might be very different from what we know it, and perhaps even finding chemical elements that don't exist here on Earth might be something that happens. So we'll hold on to that for a minute, because I think Mercedes will have something to say about that in a little bit. But I love hearing about that, right? This idea of what can't we even begin to imagine yet, because we don't know what it could be yet. Mary, any other thoughts here? Things you're seeing bubbling up in the chat?
Oh, there's some Carol is saying, is thinking of the James Webb Space Telescope and whether it will show the composition of atmospheres. So I think of these other worlds, and I think Mercedes may have something to say about that in just a little bit. Carol is asking Mercedes for when you get to your presentation, what will the Webb telescope be able to show, oxygen or just CO2 and water vapor? So there's a question about that.
The other things that I think of, we talked a little bit about science fiction in big movies or TV shows, but there's also opportunities for students to be the creators of science fiction. When I start thinking about alien worlds and exoplanets, having students draw planets that they've seen, have been discovered. What do they look like? Are they water worlds? So the creatures, inhabitants have to live underwater at all times. Are they really dense? And so the large animals, maybe there aren't any large animals because they can't deal with the gravity on those planets. And having students not only imagine them, but perhaps draw them or create books and describe them, or short stories describing these planets. I think there's some really exciting opportunities for imaginations to start really diving in and diving deep. What about you, Mary?
Yeah, and imagination is definitely key to scientific investigation. And so using all of ourselves, all of our students' selves, bringing their artistic imagination, their visual imagination, their literary imagination. The poster on the screen is actually from a series of NASA posters where an artist is imagining what it's like to be on a particular world, in this case, a world discovered by the Kepler Space Telescope and numbered 16b, not a particularly creative name for a planet, but Kepler 16b actually has 2 stars. And so this artist is imagining what it's like to have 2 sunsets on a planet. There's also actually something in this image that's a little uncomfortable for me, this idea of an astronaut exploring, and I think of speculative fiction and some science fiction that actually kind of questions this idea of, can humans explore other worlds, other lands without colonizing them? There's some issues around what does equitable science and space exploration look like that are coming up for me, even with just this image. So lots of different interdisciplinary connections.
All right. So there's still lots of great conversations happening in the chat, but I think we'll hold some of these for later. I highly suggest you read through what's coming through from your fellow educators and participants, because it's really exciting to see these coming through. But we're going to dive into some science content now. We've spurred our imaginations, and now we're going to dive into some content. And Mercedes is going to give us, oh, they can't see each other's comments. I forgot about that. I'm so sorry. We'll share some more later, I promise. But I'm hearing things about technologies and the such. I've just been reminded. Mercedes is going to dive us in to the search for exoplanets and other life and tell us a little bit about that. Mercedes, I'll let you take the wheel.
Yeah, thank you, Erika. And thank you so much for this back and forth. I mean, just sitting here and listening to the two of you talking to each other, and I'm getting a sneak peek of the questions from the audience, which I cannot see, but like people will tell me those questions at the end, and I will be able to answer them. It sounds like really fun. I will bring us back to pretty much just the facts, just to give you an idea of like what we know right now. And actually, how are we finding exoplanets, and how are we characterizing them, and so on. So at the beginning, you will see a little bit of a very basic description of what is an exoplanet and how we find them. And then towards the end, I will actually answer some of the questions that people were asking already, or, I can not tell you everything yet, but I can tell you that we have a lot of exciting stuff happening right now with James Webb. Next slide, please. So here, I thought that the best way to start this is to show you up front a summary of what I'm going to tell you about. And so, I will start just by telling you what we call an exoplanet. Then I will go into how we find them. I will explain briefly to you the two main methods that we have right now to find them. And the reason why I'm going into that a little bit is to basically give you an idea of what we get out of those methods. And that's how we kind of start to know how the planets look like. And then I will dive deeper into how do we actually figure out what these planets are made of. So if you go to the next slide, please. I will try to answer briefly the question of what is an exoplanet. I'm pretty sure most people in the audience know what an exoplanet is, but I always find it interesting to kind of like go back in history and, think like, exo comes from the Greek outside, and planet is basically wanderers, right? So exoplanets are like wanderers from the outside. And basically, if we translate to nowadays jargon, what we are telling you is that these are planets that we are finding orbiting around other stars, stars other than the sun. So we basically have the planets in the solar system, and then we're looking for and finding these planets that are orbiting around other stars near the sun. And as Mary was saying earlier, we have found so far about 5,000 of them. This field is fairly new. The first planet, as Mary was showing, was discovered in 1995, in the early 90s. So we're still learning how to do this, and we're basically finding more and more of these planets. So next slide, please. So then you probably might be asking yourself, okay, yeah, but how do you find these things? And, we basically have several ways to do it, but I will describe to you here briefly the main two methods that we have that so far have been the most successful ones. And I will tell you what we get out of these methods. The first method is called the transiting method, or the transit method, which basically what we look for is we monitor light from hundreds of thousands of stars continuously over a long period of time. And we look for these little dips in light, coming from the star, like basically these little eclipses. And what those little eclipses mean is that a little planet is going in front of the star. So we basically look for two things. We look for the size of those little dips, and that size actually tells us how big the planet is. And then we also look for how often those little blips happen. And that tells us basically how far away the planet is from the star. And we use that information to tell you, to get an estimation of how hot that planet is. And that is important later on for things like, estimating if that planet could be habitable, or, if it is a hot Jupiter, that kind of information. Next slide, please. The other method that we have is called the Doppler shift method. This method is older, but it's now less successful than the transit method because it's a little bit more complicated. So here what we do is, we look at the star, we take the light into the telescope, we put a prism and we disperse that light into different colors. And then we monitor how the colors of the light in the star shift back and forth, like towards the blue, towards the red, towards the blue, towards the red. And if the star is doing that, what you are really seeing is the effect of a little planet right next to it that is pulling the star. So the gravity of the planet is pulling the star a little bit, and the star is wobbling back and forth with respect to us looking. And what we see is the stellar light being Doppler shifted towards the blue and towards the red. And by how much that light gets shifted in color, we can tell you how heavy the planet is. We can tell you the mass. So that's the main information that we get from these methods. We discover the planets, we can tell you the size, we can give you an estimation of how hot the planet is, and we can tell you how heavy it is. Next slide, please. So why are those parameters, especially the size and how heavy they are, so important? Well, the reason for that is that if you take the size of the planet and you take how heavy it is, and you combine those two parameters, you can figure out how dense the planet is. So by knowing how dense it is, you immediately know if you're looking at a Jupiter-sized planet, or a planet like Jupiter, Saturn, Neptune, Uranus, what we call the gas giants in the solar system. From the transit method as well, we can tell you what's the approximate temperature, so you know if it is a hot Jupiter or if it is something colder. And also from the density, we can also tell you if what you are seeing instead is a rocky planet, something like Earth, Mars, Venus, even Mercury. I mean, we haven't discovered a Mercury yet, but we're getting very close to it. Next slide, please. So we have gotten really good at this. I mean, we have mass, radius, and temperature estimations for like thousands of planets now. So the next thing that we want to do is to tell you, it's like, okay, what are these planets actually made of? And that comes back to the questions in the chat already. What do you see in those planets? So basically, the way we do this is using this technique called spectroscopy. So this is similar to what I was showing you before, like how we measure the wobble of the star. We basically take the light from the star, we disperse it into all its colors, but here's the difference. We do it when the planet is going in front of the star. So you can basically see the light from the star that goes through the atmosphere of the planet, and any molecules in that atmosphere will absorb the light. So when you look at the colors of the light, some colors are going to be missing, and then you say, aha, there is water, there's methane, there is carbon dioxide, there is magnesium silicates, who knows what, but that's how we do it. Next slide, please. So as Erika and Mary were saying at the beginning, things changed 2 weeks ago. I've been working on this for years, like 15 years, and getting a data set used to take years, like just to figure out what these planets were made of. What you're seeing here, probably if you were following the James Webb press release 2 weeks ago now, what you're seeing here is the first spectrum of the atmosphere of a gas giant planet. This is a hot Saturn, observed by James Webb. I can tell you right now that from the time that James Webb collected this data to the time that they produced this result, it took a day and a half. And you can see all kinds of things here. Like you can see all these bumps, and all these bumps is actually basically how we represent the absorption of the light. So, a bump up means that we have less light in this case. And you can see that many of these bumps correspond to water, because we know that those are the colors of the light that water absorbs. So this particular planet has a lot of water. And we did this in like not even 2 days. So this is where we are right now. Like we can do gas giant planets basically in a matter of days with James Webb. And obviously, us as humans, we're always going to go farther, right? So now giant planets are easy. Okay, so we are ready to do terrestrial planets now. So what are we going to do next? If you go to the next slide. I cannot show you a result yet, but I can tell you that on July 11th, James Webb observed for us the atmosphere of the first terrestrial planet. It's a planet the same size and the same weight as Earth. It's a little bit hotter. It has a temperature of about 150 Fahrenheit, so we would be a little bit warm in that. But we have data ready, and as we speak, my group is analyzing this data, and this is the first terrestrial planet observed. And what we are going to look for in there are molecules like the ones that I'm showing you in this diagram, like methane, water, carbon monoxide, carbon dioxide. I can talk a little bit about the oxygen later, but those are the kind of molecules that we're going to look at. There might be other features in there that we don't know where they are coming from. We're also going to look at those, but there's a lot of work behind the scenes to figure out what molecules could be producing those bumps. But I can tell you right now that we are already doing this. And right now, if you move to the next slide, which is my last slide, I can tell you that as of today, James Webb is scheduled to observe 10 terrestrial planets and about 40 gas giants A lot of them hot Jupiters, like the ones that you're going to see next, and Mary's going to tell you about. And and this is just the beginning. James Webb is going to be working for about 20 years. We already have discovered about 100 terrestrial planets. So hopefully within those 20 years, we will be able to observe all of them, and we will discover more of them as we go. So my prediction right now, and I'm happy to answer any questions from people, is that within the next decade or even 15 years, we will probably be in a good position to say that we have found, biomarkers, like molecules that could indicate life in a terrestrial planet. So that's what I had for you, and I'm happy to answer questions now.
Thank you, Mercedes. That is incredible and so exciting to hear. We had the start of a question previously at the start when we were imagining other worlds about asking if water is still the big precursor for life on other planets. Could you tell us a little bit about that?
Yes, I can tell you a lot. So right now we are starting from the basics. Okay, so we know that water is a big precursor for life on Earth. That doesn't mean that it has to be a big precursor for life for like any type of life. So right now we're basically starting from the basics, from what we know, and we're looking for something like water. But 10 years on the road, 5 years on the road, I might be coming back here and talking to you again and say, oh, we actually discovered another molecule that could be a precursor for life. For example, Titan in the solar system. People think that there might be some methane oceans in there. So, it could be the precursor for life in Titan is methane. We just don't know yet.
Great. Well, that's exciting then, right? We don't know what those precursors are, and you're kind of exploring what's possible. We're still waiting for some questions to come in from the group out there watching. Mary, do you have any questions? I know I'm sure I could come up with some, but I know you always have some exciting questions for Mercedes.
Yes, Mercedes, I'm kind of blown away to know that you already have data from James Webb on a terrestrial planet. I think that's amazing. You mentioned that it was 150 degrees, so it's a little warmer than Earth. So it's kind of global warming is in place. Does that mean you would be looking for methane and carbon dioxide in the atmosphere?
Yeah, we would be like, in principle, we are being very, atheist about it. We're just looking at it. Not atheist, agnostic is the word, right? We're just looking at it, and we kind of know at what colors the different molecules are going to absorb light. But in principle, we could be seeing other things at those temperatures. We could be seeing ammonia. We could be seeing some, like nitrogen oxides. We could be seeing magnesium silicates, which is one thing that is, everybody's thinking about the terrestrial planets, but I'm coming to this field from the angle of what are planets made of, so big planets are super exciting for me as well, because one of the things that we have been doing for many, many years is trying to figure out what clouds in planets are made of. And one of the candidates is this magnesium silicate, which is, I can't picture in my head with it, but it's basically like small rocks floating about, and they form clouds, and we can't see anything through the atmosphere. And we have been stuck with that, like with Hubble and big ground-based telescopes for a decade, because we couldn't figure out what those things are made of. Now with James Webb, we are going to get observations in the infrared, which can actually see through those molecules, and they can tell us if those molecules are there. So there is a lot of really interesting stuff going on. Like, we're going to be able to tell you, like on Earth, all the clouds are made out of water, right? But maybe these other planets, especially the gas giants, like hot gas giants, they're going to have these clouds made out of like diamonds, like, like all this like sapphire, that kind of stuff, which is really cool. So yeah, we're we're going to have all those data coming. So very exciting.
That is very exciting. So I think I'm going to take one more question now. We're going to have another opportunity at the end for a few more questions, another Q&A at the end. We'll go with a question from Kimberly, I think is pretty pertinent here. Since the light we're seeing from the James Webb Space Telescope is from years ago, as many say, telescopes are time machines. Does that mean the element signatures we're seeing for water is also from that time ago?
Yes. But in the case of exoplanets, we're lucky here. Okay, so when people tell you about, these telescopes, in this case, JWST, looking back in time, and they tell you like, we're looking back like 13 billion years ago. Okay, in the case of exoplanets, we need so much light to detect these signatures. I mean, we are detecting, okay, for a planet like Earth, the signal that you're seeing is one photon being absorbed by the atmosphere of the planet out of 1 million photons coming from the star. So we need a lot of photons for this. So what that means is that the planets that we look at are very, very close to us. So in principle, these are things that are only like, 20 light years away. So the signals that you see, they're older than the present, but they're only like, like a few years older. They aren't like 13 billion years older. So, if there is life in that planet at the time that light, went through it, I'm pretty sure that life's still there. So that is one exciting thing of studying exoplanets versus studying galaxies that are very far away.
That is very exciting. Thank you so much, Mercedes. We have plenty more questions, and I think we'll save them till the end because we want to introduce all of you out there how you can start involving your students in this really exciting cutting edge research. So we're going to put up our first slide, our next slide. We're going to explore alien worlds in the classroom, and I want to introduce you to the DIY or do-it-yourself planet search portal. Next slide. DIY uses a telescope network called the Micro-Observatory Robotic Telescope Network that's run out of the Center for Astrophysics. On the screen here, you're seeing actually our splash page for the Micro-Observatory telescopes. And you can see there's actually a number of interfaces for engaging with our telescopes. Those of you out there, there's also an address on there, microobservatory.org will get you to the splash page for all of our interfaces. And using these telescopes right now, any of you can access them online and observe exoplanets with our DIY, what I'll tell you about today, but galaxies, the moon. So there's many investigations you can run in your classrooms today using these various interfaces. And one thing you could do right now for the next couple of days, actually, is the NASA's Astrophoto Challenge is right there on the screen there. And that's an opportunity to observe the Eta Carina and the Carina Nebula, which you might be a little familiar now if you've been following the James Webb releases, because they actually just released an image of that nebula. And observe it for yourself using Micro-Observatory, or actually process data from some of NASA's other great observatories and submit it to the challenges for some chances to have commentary on your images from NASA scientists and experts. But we're going to dive into DIY planet search right now. So next slide, please. All right. The DIY planet search is an online lab. Here you see our front page. There's opportunities to explore exoplanets and science facts on the page. And in a little bit, Mary's going to tell us about the tools themselves that are going to engage your students in this search for exoplanets, where they'll have an opportunity for real authentic investigations, taking live data from our telescopes and processing it just in some of the ways that actually Mercedes explained to you. So the next slide. In DIY planet search, students use the transit method that Mercedes kindly explained to us. They use that model to explore the light that comes from stars. And as Mercedes so kindly pointed out, these are just a few dots of light, right? We're looking to gather as much light as possible. But when we're exploring exoplanets in the DIY planet search, we're looking at just a few pixels and looking for that signal as the planet passes in front of its star and that light dims, as you can see in the graph on the lower front of this screen here. Mary, is there something you wanted to make sure folks know about exoplanets here and how we're discovering them on DIY Planet Search?
Just to point out that a little earlier, Mercedes showed a transit light curve like the model here from James Webb Telescope, and it looked just like this model. It kind of is steady while the planet is not in front of the star, and then the brightness goes down when the planet does cross in front of the star and then goes up. And I want to point out that this is the fact that the James Webb data looks just like the model is amazing. Because in fact, in our online lab, we're going to have to work with a little bit messier data, which is true when you're at the limits of your technology. And so we'll take a look at what it means to have messy data.
All right. Thanks, Mary, for that little extra addition of messy data. That is really important for the classroom. Can we go to the next slide, please? So as we mentioned, your students get to use the Micro-Observatory Robotic Telescope Network. And in fact, they're actually going to be using a particular telescope in the network called Cecilia. Cecilia is named after Cecilia Payne-Papashkin. And all of our telescopes are 6-inch telescopes. And Mary's going to tell you a little special fun fact about Cecilia.
Yes, well, that's a picture of her behind me in my office here. And in fact, the office I'm sitting in was Cecilia Payne's office at the Center for Astrophysics. So I feel a particular connection to that micro-observatory telescope and that particular astronomer.
A famous astronomer. I highly suggest you look her up. There's some great resources on the Smithsonian Learning Lab telling you a little bit about her. And these telescopes are located at Amado, Arizona, at the Whipple Observatory run by the Smithsonian. So that's the telescopes you and your students are going to be using to take your own images of exoplanets. On the next slide here. But what does that mean for your classroom, right? There's actually a lot of really great connections for your classroom. We, in fact, investigate many standards. Sorry, I lost my place here. So your students will engage in virtually all of the elements of scientific practice engaging in the DIY Planet Search portal. They'll ask questions and define problems as they go through the challenges of detecting an exoplanet. They'll develop and use models to evaluate their analysis, their data collected. And they'll plan and carry out investigations, which Mary will actually describe for us in a second of what that process is going to look like for your students as they go through detecting an exoplanet, or measuring a star, I should say, in the hopes of detecting an exoplanet, and analyzing and interpreting that data as it comes through to determine if they think there really is a planet there. Mary, do you want to add some things here on the cross-cutting concepts or some of the core NGSS disciplinary ideas?
Yeah, so the thing about exoplanet science is, even though it's, only 25 years old, it's Nobel Prize winning discoveries, right? The finding planets around other solar systems, but the concepts behind it are very understandable and are part of the basic science curriculum. The idea of orbits, understanding that objects that orbit more closely to their star go faster than things out further, understanding the system and its size and scale and proportion, and kind of interpreting, doing proportional thinking to understand that dip in the light curve is proportional to the size of the planet going in front. So there's a lot of integrating your mathematical thinking with your systems thinking with science concepts that students get to apply in doing work and detecting exoplanets, a task that we didn't even know was possible until less than 30 years ago.
All right. Thank you, Mary. All right, next slide, because we've got only a little time left and we want to dive in and show you what this interface looks like. So what does going through the DIY Planet Search look like for your students? First, they're going to use the telescopes to take multiple images of your alien solar system. Then they're going to measure the brightness in each of those images. You're going to display and interpret your results. And then you're going to deduce the planet size and orbit. And Mary's actually going to take us through this briefly and show us some of the ways that these connections for your classroom. So next slide, Mary, and show us the tools.
Great, thanks, Erika. Yeah, I'm actually going to give kind of a whirlwind tour of the DIY Planet Search interface, in particular pointing out its power for helping students learn, and kind of trying to whet your appetite to go try it yourself and learn more. So in particular, next slide, please, the DIY tools allow students to do all those scientific processes, a full investigation of a real exoplanet. So the DIY interface allows you to schedule, as you can see, schedule observations using the Micro Observatory telescope. Almost every night of the month, we have a different target scheduled, and all of these targets are hot Jupiters. They're, in order for small ground-based telescopes to detect that dip, the planet has to be pretty big and pretty close to its star. But there are lots of those planets. In fact, those are the easiest planets to have been discovered and to detect. So your students have a good chance of detecting a signal. Next slide, please. Once they choose a target, they have typically these eclipses take place in a single night, so your students can collect about 100 images and you can apportion them among your students. There are tools and guides for educators on supporting a classroom of students to do this. Next slide, please. You can tell the telescope an exposure time. The brighter stars, you have a shorter exposure time. The dimmer host stars of a planet, you have a longer exposure time. Next slide, please. And then you get your 100 images back for your classroom. And the most important innovation of the DIY Planet Search online laboratory is that we've created a complete data analysis environment in the browser. And so your students will get to use professional tools and techniques, the same tools and techniques that exoplanet scientists use to characterize the size, the orbit of a planet just from the light curve. So here's what an image looks like. And it looks like a bunch of white dots. There are tools for helping students find, next slide, please, which of those dots is the target star. Next slide, please. The key thing that students come to understand around that standard of understanding instruments and instrumentation is, while it's great that we get those gorgeous images, and it's important, and we learn a lot from gorgeous images from telescopes. In fact, it's the numbers behind the images that are so important to doing science. The fact that what actually comes back from the telescope is a bunch of zeros and ones representing how much light there is. And students in this browser can measure the brightness of the target star over time. They learn about important ubiquitous science concepts like how do I know that the brightness change I'm measuring isn't because of a cloud? Well, you need some controls, and so you compare the brightness of your target star to two comparison stars. And the next slide will show you, if we could play this movie, we'll show you some of the tools inside the browser that help your students identify which one of these stars is the target and which is the comparison. We have a little finder chart that they can place over the image, and then we'll get rid of that finder chart and remember that pattern so that you can place the measuring circles, which are tools for measuring the total amount of light that the target star is emitting and that two comparison stars. We've tried to make the interface accessible. You'll notice the different colors are also different shapes so that students who may be colorblind can kind of distinguish the target star from the comparison stars. And you'll see the numbers changing as we calculate and record the brightness value, which is 0.79 for this target star. And the tools in the browser actually graph that measurement for you. So students can very quickly measure the brightness of a star purported to have a planet orbiting around it. And if we go to the next slide, over time, as students measure a few stars, they start to see something. It's a little hard to say here. Have I got any pattern? I'm not sure yet. And so one of the things students learn is that more data is better, right? You don't, more data is always better. You find more patterns, your statistics are better when you have more data. And so the next slide shows you a classroom's worth of 100 measurements, 100 measurements over a period of 5 hours of this star. And you can see there really is a dip in the brightness over time. Although it definitely looks a little messier than the dip that the James Webb Space Telescope measured of that hot Saturn that Mercedes showed earlier. Nonetheless, your students can collaboratively, in just a few class periods, generate a light curve and then interpret it. On the next slide, you'll see some of the interpretation tools in the DIY Planet Search, because it turns out that the shape of the light curve, whether it's a V shape or a U shape, tells you something about the orientation of the orbit. The width, the duration of the light curve tells you also about the distance of the planet from its star. Closer planets have a shorter duration than farther planets. And then that depth, that all-important depth, if we go to the next slide, you'll see that we can actually calculate, and this is where proportional thinking comes in. So students can actually get a measurement that shows a result of the size of that planet compared to its star. Is it 1/5 the size of its star? Is it 1/10 the size of its star? Students can come up with results. Typically, students want to ask, is it the right answer? Did I get the right answer? And we always say, nature doesn't have right answers. You can't look up the right answer. You only get results. And the question is, can you justify your result? Can you say that your result is strong based on your data and evidence and based on the model? One of the things in DIY Planet Search, and sorry, where Erika, did you want me to?
Mary, we only have 30 seconds left.
Okay.
So on the next slide, you can see where that all of our students and participants around the globe are sharing with us, and we hope you will as well. Share your data with your class from your classroom onto the DIY Planet Search portal.